on phase change materials used in residential exterior wall retrofits. And I'm going to present today along with Aref, and also the node Marianne has been an integral part of this project. Also want to acknowledge the work of grad student Austin Marshall, Derek Ross, a previous WCEC employee, and Shabankar, who's a graduate of mechanical engineering. So talk about what the processes we're looking at here. So this was a project sponsored by the California Energy Commission, and the goal of the project was to come up with a retrofit solution for residential homes that are older and were built without insulated walls. So this was standard practice prior to like 1978 was when the energy standards went into effect, requiring insulation of walls. So basically what you have is you have some exterior siding like stucco, generally perhaps a layer of plywood, some wood studs, normally 2x4s. We're showing 4x4s here, and then like empty air cavity, and then some gypsum drywall on the inside wall. So the process that we came up with here, we sort of modified a standard installation process. So when you're insulating these walls, generally what you do is you put like 1.5-inch holes in the drywall from either the inside or from the outside. You pump insulation into those walls, and then you seal those holes and paint them. The modifications that we did was we used an aerosol sealing process we'll talk more about later to seal the envelope before we put the insulation in. And then on the interior side, after we seal the holes, we put a layer of phase change material and then some gypsum, a fresh layer of gypsum. And that's the process. Sorry. Yeah, no worries. So just a quick overview on what phase change material is. So it's basically a material designed to change phase at a temperature range that's advantageous for thermal energy storage. So for example, ice is a phase change material, but it changes phase at 32 degrees Fahrenheit. Instead, we are looking at materials that change phase closer to 70 degrees Fahrenheit, which is an advantageous temperature for buildings. So for example, here's a diagram of the benefit that we might see in the winter. So it's a cold day and we still get a lot of high solar, it's a cold sunny day. So we get a bunch of radiation on the exterior wall. It warms the phase change material, and some heat makes it through into the building, but a bunch of it gets stored. The PCM starts to melt, storing more energy. And then at night, when the solar radiation goes away, heat is rejected outside, but since there's storage in here, we still are passing some heat into the space. So basically, what's the question? What are the struggles? Like, why is it hard? What do we not know about this process? The trick is characterizing how the phase change control is going to perform. And then, first of all, do we understand exactly how it's going to perform, and then how well can we model it in typical energy simulation software? Because that's essentially what we need to understand how it's going to perform across the state or across the country, and what the energy benefits might be, and should this be something that's like standard part of building code. And so those are the questions we're trying to answer. And so the steps that we're taking to that are a combination of modeling, laboratory testing, field testing, essentially to try and close the loop between improving models and understanding the accuracy of those models and being able to forecast impacts. So we're going to show you these. We're going to show you how far we've made it through that process today. We are working with simplified energy plus models, which are basically one-dimensional building simulation models. And so what we want to understand is how well these simplifications in energy plus software represent what the actual behavior of the phase change control is. And so in order to do that, we're comparing our energy plus models to laboratory testing and more sophisticated simulations. So basically finite volume models, and to understand how close the energy plus model represents real world conditions. And then we're conducting 3 field tests in homes across California to look at how, 2 things basically, like how feasible is it to really install this material as a retrofit and go through that whole retrofit process I showed you, and then how well does it actually perform. So, yeah,
I am so sorry I came in late.
No worries.
And then rudely want to ask just a question you probably already said immediately.
okay.
Who funded this one, Theresa?
This is funded by the California Energy Commission, so we're specifically looking at the impact of this retrofit for California clients.
And this was through which program or?
Here, they're very focused on natural gas,
The what?
natural gas energy research. Yeah. Okay, so the most unfortunate thing I have to tell you today is that I'm not going to be able to give you all the answers to the research questions yet. We're not done. But what I am going to be able to tell you today is tell you about our project report approach and our laboratory apparatus. We're going to be able to give you some very detailed results for how the walls are performing without phase change material. And then we're going to have a discussion of the PCM modeling and where we are at on that. And then hopefully we'll come back next spring and we'll give you all the answers. So somewhere I heard once, nobody wants to hear how hard you work, they only want to know the answers. But today we're just going to tell you how hard we work.
Okay, so I just want to kick it off with lab testing and modeling flow chart. So it's a fairly linear process. We start with the wall geometry variation. So we have two. We have baseline, which is essentially just a standard wall based off DOE recommendations. And we also have PCM, which is just the phase change materials installed on top of that baseline wall, as we showed before. For those wall geometry variations, we go ahead and move on to the 1D Energy Plus modeling simulation. So we go ahead and build that and try to get as close to recommendations as possible. And from there, we're able to derive different profiles and results that we want to further validate. So after that, we move on to the 3D finite volume modeling of the wall on the select days. So we pick different days that represent the season specifically. And we want to do a more in-depth 3D mesh analysis of those days in order to make sure that the simplifications that Energy Plus uses are valid. And if that's validated, we're able to move on to the lab test wall. So we go and build a wall specimen, put it inside of the wall test apparatus, and test further to make sure that it's valid in real life situations. Now, if either of those don't match what we expect in terms of flux results, we go back to step one, which is the 1D energy whole building model, and refine it to make sure that everything is good and try to match more closely with what we'd expect, and progress further as we're able to succeed with the higher fidelity tests. Once those are complete, we're able to move on to
Just forward arrow, or do you want the light?
Yeah, how do you do the light?
Top, it's on the top.
Yeah.
Give it upside down.
Oh, there we go. Okay, so we compare the heat flux results that are output by Energy Plus, compared against the finite modeling, and move on to laboratory testing. And if everything is good, and if everything compares well with the higher fidelity models, we're able to move on to the analysis of the full year energy impacts. Now, we are currently right around here, building the different models, but we're expecting to move on to the analysis of the full year energy impacts.
Question.
Yeah.
When you're trying to align your modeling data with the performance data from the demonstrations, how does the fact that you've chosen to seal the home first come into play? You know what I mean? Because like you're not just testing a standard wall versus a PCM wall.
You'll see more details, but all of this process is only about the heat transfer just through a wall section. We're not talking about the whole house yet.
Okay. Cool.
Okay, moving on to the construction. So we're going to go ahead and start with the baseline wall. So that's the typical wall that you'd find in any home. That's insulated. It's either insulated or not insulated. So we start with the baseline wall model. That's again based off typical residential wall. Studs spaced about 60 inches apart. It starts with a stucco layer about 0.875 inches, moving on the plywood. Then a stud / insulation layer. We call that a consolidated layer. And then moving on to the 0.5 inch gypsum. And here is our construction for the actual apparatus. So when we were doing the analysis, we wanted to make sure that we were modeling the entire wall, not just a cross section of the center. So we took into account the different ratio of wood to insulation / air, the center area that you find typically in a home. So we're not just talking about the center area, we're also talking about the top framing, bottom framing windows. That typically went out to about 20 to 25% wood. So what we did is we took a ratio of 22% and went with that for the laboratory testing. And to do that, all we had to do was increase the stud sizes from 2x4s to 4x4s, which is actually 3.5x4. Okay, going on to the Energy Plus model. So in general, we built a pretty simple house to represent a very generic single family residential home. It has 3 thermal zones, occupied space, crawl space, and attic. It has about 81 centimeters squared of conditioned floor area with 20% of the exterior surface being windows. It has a single speed air conditioner with 3.4 COP at 35 degrees Celsius and a 25.5 cooling set point. And we also have a natural gas furnace with 0.78 fuel utilization efficiency at 19.5 degrees Celsius heat set point. This is all based off typical residential homes for this area. And we built this in SketchUp over here for use in Energy Plus. Okay, so moving on to the actual details of the Energy Plus model, we have a conditioned space effective area of 634 centimeters squared, ventilated attic and crawl space leakage of about 400 air changes per hour, about 3,375 and 4,115 centimeters squared, respectively, attic to crawl space leakage. We have an attic insulation of R38, floor insulation of R19, very well insulated for the house. The next thing was building internal mass. This we used about 2 times the square footage of the occupied space based off DOE. That is, this greatly affects performance of the PCM. That 2 times number. This is what is recommended currently, but we definitely want to investigate this one. And then internal load schedules, electrical equipment intensity and gas intensity were based off these resources. Typically DOE, but implemented by, again, what's standard.
Question.
Yeah, please.
One of the problems with Energy Plus is it often, well, it auto sizes the systems.
Mhm.
Did you pin down the sizes or did you let it do the auto size?
I think we might have the other side.
You know, it's been a while. I would have to look.
Yeah.
That could have an important
Mhm.
implication for you.
Yeah, a lot of the initial model development was done by Derek Ross, so we're gonna have to refresh ourselves on what that was built on, but I'm pretty sure it's out of place.
We're not to the end of this yet, but early indications are that phase change control will have the biggest impact in shoulder seasons. And so may not have much of an impact on size.
And due to the 1D nature of Energy Plus, it makes it difficult to model that consolidated layer, so that stud insulation layer. So we had to do some manual calculations to get the properties needed, specifically thermal resistance, density, and specific heat, which are needed for material properties. We just did a general circuit analysis to be able to find a combined material property values for that specific layer. Okay, going on to weather simulation. So weather files for Energy Plus simulations were used from California weather files from the California Measurement Advisory Council. CZ 2010 were used for the initial development, but we're planning to switch over to CZ or CZ 2022, I believe. Once we have the verification going on, just to have more current weather data. And we use the data from Sacramento to generate wall temperature outputs for the 3D finite volume analysis, as well as the laboratory testing, just for verification purposes. The weather file was modified, to pick 3 specific days that we found to be the most characteristic of each season, and those were repeated 3 times within the weather file. We did that specifically so we could have a input and output that was similar, which was required. So we needed similar beginning flux and end flux. in order to have consistent boundary conditions for the fluent and the laboratory testing. So that's what we did there. We picked January 31st for winter, March 8th for shoulder, and August 4th for summer. Okay, moving on to the 3D finite volume modeling for the baseline. We use ANSY's fluent finite volume simulations to conduct and validate the composite quantity material properties and energy plus heat flux results. And we leverage symmetry just to ensure that we have minimal computing time. So again, data from each day was input as boundary conditions for the model. So we had the outdoor temperature on the outdoor side of the wall, indoor temperature on the indoor side of the wall, and we measured flux through key points of the model and verified that against the energy plus outputs. We did that for 4 days total in order to get a repeated cycle, as we mentioned with the repeated days earlier. And we took data from that third day and compared it against the third day at Energy Plus for verification purposes. So this was repeated for 2 fluent models, one with that blended consolidated layer and one for that separated consolidated layer. And we did that just to ensure that that 1D assumption in Energy Plus was actually an okay assumption to make, an okay simplification to make. And this just goes further into the model development. So you can see here surfaces 1 through 4. So 1, 2, 3, 4 were just essentially insulated edge surfaces. Oops. 5, which is that back area right here, is the indoor wall surface, and 6 was the outdoor wall surface. So we did that just to get essentially flux going straight through. Moving on to the laboratory testing and dynamic heat flux measurement. So what we wanted to do was get essentially a dynamic heat flux load onto the wall sample. So we wanted to measure the results from that compared to Energy Plus, similar to what we did with the 3D fluent modeling. So we have 2 dynamically controlled thermal plates, right here and right here. We control the temperature of that plate using TECs, thermoelectric coolers, which are essentially resistors that are able to heat one side and cool one side depending on the voltage output. So if you have a positive voltage output, you're able to get a hot side on the bottom here, cold side on the bottom here. But if you were to reverse that voltage output, you're actually going to flip the temperature sides. And we also have a water cooling circuit on the other side to pull heat away from the hot side just for better cooling. And that allows us to heat up these plates and effectively like model the exact temperature from Energy Plus on the interior and exterior of that wall. And essentially trying to get the heat flux from everything. All right, so here's a more in-depth example of the how everything is set up. So we have an array of roughly, 20 for the outdoor, 40 for the indoor. TEC circuit spaced strategically along the plate in order to give us a widespread, like easily controlled temperature profile. We also have a series of 5 thermistors located on each circuit in order to provide feedback to tell us exactly how much we need to heat or cool the TECs. And I didn't mention this earlier, but each of these, so we have 5 total TEC circuits, each controlled separately by their own controller. So we can focus what part of the plate needs specific heating or cooling. Just so we can have better control of the plate instead of having an overall plate temperature. Oops. In addition, we had 3 flux sensors, TE-Tech Ultra 09s, very high, very high resolution heat flux sensors placed strategically in the center and on both studs, just so we can see the difference between different locations and where we place them. And over here, you can see our water cooling setup. We have water that's spread over these circuits just to cool and boil heat, just so the TCs can operate as they should. Okay, laboratory testing and controlled data acquisition. So we use a combination of National Instruments hardware and software, specifically LabVIEW control. So what happens is Energy Plus, we input that profile, what happens in LabVIEW, input that profile from Energy Plus. That communicates to the controllers using a serial protocol and tells it essentially a set point. What is the desired temperature that the plates need to be. And those controllers have inbuilt logic that's able to calculate the voltage output for the TECs and heat them or cool them accordingly to match those set points. The thermistors then measure the temperature of the plates on a specific circuit that it's in, send that feedback back to the controllers, and then adjust the voltage output. For data acquisition, LabVIEW software reported all data available to the controllers. So the controllers themselves have input data measurements. So whether it's voltage output or the temperature from the thermistors or whatever, they send that back to LabVIEW. We report that ourselves, and then all analog data is measured measured from the heat flux sensors and thermocouples, water source temperature, and room temperature sent through the NI hardware back to LabVIEW using the internal program. Okay, so going on to our laboratory testing and baseline control results. So again, we did it for 3 days specifically. So 3 days specifically to measure the 3 different seasons. We have winter, spring, and summer. If you look at these top graphs over here, you're able to see essentially how close we're able to match the temperatures desired from Energy Plus with the actual temperatures of the wall. So these orange curves right here, that's the outdoor temperature that ranges roughly 7 to 50 degrees Celsius, with the indoor temperature stabilizing around, I would say, 18 to 23. And you can see we match fairly closely. We're able to, using a temperature curve percent error, we're able to get roughly 1% for both the indoor and outdoor. Obviously, indoor is easier to match just because it's a smaller temperature spread, but outdoor we're still able to get within 1.2%, so fairly accurate. Moving on to the actual results and the comparisons. So this is for the winter flux comparisons. So there's a lot of information. So if we look at the blue squares, this is what we're trying to match. This is Energy Plus. And you can see not only does the red line, which is the laboratory results, match that closely, but so does the fluent results. For both the blended, so the consolidated layer of studs and insulation, as well as the separated layer, so the stud and insulation separate. Everything's able to match that Energy Plus. Everything's able to match that Energy Plus curve fairly closely, and that's consistent for both indoor and outdoor. And again, this is the consolidated layer of, or this is for an insulation layer and stud layer. This is no PCM. Moving forward, we move into spring. Similar results. We're able to match closely within that, especially if you take into account the standard deviation and the fluent results.
So,
yeah, please.
can you just describe these shapes to me? What's going on with this shape where it goes up in the middle?
Oh yeah, of course. So this is the beginning of the day. So we have minimal heat flux moving from the outdoor to indoor. Then we start increasing that solar incident radiation on the outdoor wall. So we see more heat leaking into the inside of the house, warming it. And as the solar incident radiation goes away and the outdoor wall cools down, we start losing heat from the inside to the outside of the wall. And you see a little bit of delay on over here just because we have to, heat up the internal of the wall and transfer it over.
And what would that look like if it didn't have phase change material?
Oh, this has no phase change. Yeah, this is the baseline, correct.
Actually, let's go back to that for a moment.
Please.
I was just looking at how much power, that thermal power, that you're getting 100 watts per meter squared.
Mm-hmm.
Which I understand that would be the solar gain, the sun shining,
Yeah.
a modest sun, because 100 watts per meter squared is, well, this is a vertical wall.
Yeah.
And which direction is it facing?
This is the south wall. These are the south walls. So this doesn't have the direct, it has direct sun over the course of the day, but it's not east or west wall where it had.
But now this is the heat flux through the wall. So the solar could be much higher, but a lot of that heat is just either being reflected from the wall or radiated out. This is the part that's going in. So it has the alpha of the wall.
Yeah, I'm just trying to get the right scale here.
Exactly.
Where we're going.
It's similar.
Yeah, all right.
And you don't have the seasons here, but this was, the winter day actually has the highest because the sun's low in the sky, right? So this is winter, right here. Okay, so just to summarize what we've shown you, where we've managed to get by the time we're here is we've managed to build a laboratory, Energy Plus model, a fluid model, and a laboratory test of a wall with insulation, no phase change material. And we've essentially been able to show agreement of the various models with what we actually observe in real life. And Aref showed you that great plot of how well we get the temperature control of the laboratory experiment. It took us like a year and a half to get there. We built that device about 16 times. So we spent a lot of time getting here, unfortunately. So here we are, we're really happy with this. So then we say, okay, now we're gonna put on the phase change material into our model and onto our laboratory apparatus and essentially see what happens. At the beginning of the project, we were talking to 3 manufacturers of phase change material. We essentially lost 2 along the way. The first one, Saint-Gobain, is a massive international building materials company. They originally gave us a sample of a phase change material, a plaster with a phase change material in it. And then if they ended up discontinuing that due to a formaldehyde emission concern, as I guess as the product dried. Anyway, they weren't super clear, but they said, sorry, no more. And they have since exited that market. Encode is a small startup company that's gotten a lot of federal funding, as far as I can tell. But what they have isn't commercially available in large quantities. And we tried to get a sample for laboratory testing. We got one, had a leak in it. We weren't able to get another one. So we have essentially been unable to test that. Insul Corp, we should have just brought one with us.
That's
Yeah.
Go fetch, go grab it.
Yeah, can you go grab it? Robin?
Where is it in the room?
Are they in the lab? Where's
I have
the
one,
box?
I have a box in my office, yeah.
Okay, so Insul Corp is a plastic panel that contains phase change material in these big squares. We'll bring one over to show you. It's commercially available. They've been marketing it for a while. Mostly they use it above drop ceilings, and so we're investigating here for the purpose of a wall retrofit. Okay, so essentially, how does it behave? So this has been one of the challenges, is that we've struggled to get data on essentially its thermal properties, specifically how its enthalpy changes with temperature. We just recently got some updated data from the manufacturer that comes from differential scanning calorimetry testing. And so basically what happens is as the material, so let's look at the red dots. This is the data that's provided to us by manufacturer. As material heats up, it starts to melt. If at any time, so it has like a hysteresis. So if at any time it then starts to cool, it then, as it changes, as it starts to cool, it stays in the same mixture of partially melted and frozen material, comes back to the freeze curve, and then it goes back down and starts freezing. So it's got this hysteresis behavior, which is typical of phase change materials. And I just have it, this is enthalpy per degree Celsius, and then I have it plotted over here, just total enthalpy. So then we can see the whole hysteresis curve. And so one of the challenges is like, how accurate is this hysteresis curve? Because, and then how well can we model it? So Energy Plus only allows us to basically have one linear curve in the enthalpy diagram. And so what we've been modeling is the dotted line, and then the solid line is what the manufacturer provided us. And so then the question is, when we then model the dotted line versus the solid line, and you know, what's the actual truth? We don't exactly know. So then how does everything line up? I think we described this earlier, but we basically just took the exterior wall and then we put the PCM panels on and another layer of gypsum. One thing is that there are air gaps in the PCM panel when it's installed on the wall. And we don't, one of the things we seek to understand is how those air gaps will also affect the total heat transfer through the wall.
Theresa?
Yeah.
Why is there gypsum, why are there two layers? of
Yeah,
gypsum?
because otherwise it'd be really ugly.
Well, I understand the gypsum on the outside,
Oh,
but.
because we're going into a retrofit.
It's a retrofit.
Yeah, so the exterior wall, the interior wall's
Got it.
already there, yeah,
Got
okay, gotcha. So anyway, so here's just a picture of it on our lab sample, installed on our lab sample before we put that last layer of drywall on. You can see these are the air channels. The air channels are really handy, we kind of need them because for installation onto the studs, right? So we have gaps we can screw into the studs. I already talked a little bit about what Energy Plus is capable of, but like I said, you can measure a history, you can model a hysteresis, but you essentially have, it's like a 4-point hysteresis is all you get. And then when we went for modeling, for laboratory testing, we made just a few changes to the apparatus. We moved our heat flux sensor so that we had one over the stud in the PCM, one over just the PCM itself, and then one here in this air gap, so we can see how the heat flux varies depending on where we are in the wall. We made a slight change. Instead of repeating the same day over and over, that logic sort of fails here because every time we go through a day, we melt some fraction of the PCM, and so it's like difficult or impossible to return to the exact point at which we started. So we decided instead we would just run a simulation of several days in a row where we see like increasing melting here with each peak. And if you run long enough, the initial conditions become less of a concern. And so this is the 3 days we ran, 96 hours, 4 days that we ran. We're switching to run longer, but I'm going to show you the results for today. And you can see again, our temperature control is really good. And then this is our results. So we're still actively working on this. I mean, we're generating more results right now. You can see the outdoor flux looks quite good. And the indoor, so each day we essentially get more melting behavior. Well, except for this one, this was this we don't get much solar. It's been a cloudy day, the model. So we track really well, except we started on this last day where we ended our test. We see the laboratory test flux result drop and the Energy Plus model not. And so, but this is where we ended and we were like, oh, so right now, yeah, so this is running again. We added another day. But things are looking pretty good. So this gives us some confidence that the material that we're modeling in Energy Plus is pretty close to what we're actually testing in the laboratory. And so this is what we've been working on and continually trying to see. I mean, the goal at the end of the day is to get the Energy Plus model to represent what is actually happening in real life. Okay, so that's where we are on the modeling, and we're going to keep going with that. In the meantime, we were supposed to do all that, by the way, before we retrofitted any houses, but it just took too long. So we went ahead and retrofitted the houses while we were trying to figure everything out. So I'll just pass back to Aref and he'll tell you about our field retrofits.
Yeah, so we wanted to get a retrofit in a multitude of climates. So we did CZ3, CZ12, and CZ16. That was Vallejo in April 2022, Sacramento in June 2022, Los Angeles, LA in October 2022. As some of you are very aware. The perimeter of, so essentially the plan of the retrofit had 5 major tasks. We had home preparation, moving everything away from the wall, selecting the different walls that we need, essentially just kind of prepping the house as you would imagine, pulling off trim, what have you. We had an aerosol ceiling, so that involved drilling holes into the wall, the uninsulated areas of the wall, pulling in our equipment and sealing it. We had two different methods that I'll explain in a little bit. Then we had the blow-in insulation, traditional blow-in insulation via wall cavities. We had some contractors come out, use the optimal insulation that we had and insulate it traditionally. Then we had the PCM installation over select walls, which we, here, I'll use this as a demonstration. We installed this exactly on the existing walls, drilling through the areas without PCM, obviously. And prepping the walls as, you know, and covering the walls as best as we could, fitting for each home geometry. And then that was followed by wall finishing, where we just wanted to return the home to as close of a condition as we could beforehand. Sometimes, most of the time, even better.
So this, are people living in these homes?
Yeah, people are living in these homes. So we found dates that were most convenient for them. Usually they're going on vacation or going to a wedding, what have you. And they're usually gone for about a week. This was about a 7-day process for each one of these homes.
And so aerosol sealing, you use Mark's technology to seal leaks?
We have a slide on each one, so why don't we
Okay.
go?
Yeah, I'm gonna go into depth on for each one of these. So this is the field retrofit preparation. So holes were drilled in the exterior walls for both PCM and non-PCM walls. So we only picked 3 walls for PCM installation, but we wanted to insulate the entire home. So we did every wall that we could put insulation in. Sometimes walls already insulated. We didn't know about, but that's fine. Walls were selected for PCM that had maximum solar radiation. So we chose typically an east wall, a west wall, and a south wall. And we tried to pick walls with minimal windows because obviously we couldn't get PCM coverage of those. And once those walls were selected, we pulled up window trim, baseboards, crown molding, electrical outlet covers, anything that would interfere with the installation. And you can see over here all the walls that are drilled into this kitchen. This is just a brief preparation. This one didn't have PCM installed. You can see the crown molding still there, but this is like what it would look like before the PCM was installed.
I'm sorry, what are the holes for?
The blown insulation process. Yeah.
So these were uninsulated walls.
Yeah.
Do you guys have any idea when Title 24 changed and made people start putting insulation?
1978.
78?
Yeah.
That's for new construction.
Yeah.
Yeah, so every home built after 1978 has insulation. So there's we have the number in a report, I can't remember it off the top of my head, but the percentage of existing homes with that are uninsulated is shockingly high. It's like somewhere between 25, it's 25, 30%, something like that.
I think it was closer to 30, yeah.
It's a big number.
It's massive.
Yeah.
I believe you had a question.
That's interesting.
How would I see that?
It popped up in the chat.
Oh. Okay, keep going.
Okay, moving on to the direct aerosol sealing. This is the first method that we did. So essentially what we're doing, we attempted this in the Vallejo and Sacramento field sites. So essentially what we did is we pressurized the entire house with a blow door fan to about 100 pascals. And what we did is we directly ducted the sealant flow to those holes that were drilled for the blown insulation. And we use the existing aerosol sealing methods to blow aerosol in and try to deliver flow to these holes. And you can see we tried to seal quite a few simultaneously to speed up the process. Unfortunately, for this method, the leaks in the cavities were so large that the pressure measured in the wall cavity relative to the outdoors was about a 50, or was less than 50 pascals, was low. It was very small. So that being said, we couldn't move enough sealant via this method to actually seal it in any sort of reasonable amount of time. It took several hours of sealing using this method to see very, very basically indiscernible results. So with this in mind, we wanted to approach it a different way, a way that was more robust and that would be theoretically faster. So that took us to the attic and crawl space sealing. So instead of pressurizing the house in this method, we actually depressurized the house. We put an aerosol injector into either the attic or the crawl space, and we released aerosol mist into the air. So what that did was that pulled the air from the attic or the crawl space through the cavities in the ceiling or through the cavities, effectively sealing those holes and preventing and essentially reducing the leakage rate. So we performed this exclusively in the Los Angeles home. For both the attic and the crawl space, we did both of them. It took less than 1 hour each. And it only took about 30 minutes to purchase it from the house after the process was concluded. So if you look to this graph over here, you can see how the leakage flow from the house drastically dropped. So with the holes not drilled yet, we had a leakage rate of about 3,293 CFM. Obviously pre-sealing, after we drilled the holes, that would increase because we had more open area to the outdoors. So we bumped up to 4,795. Post attic sealing, that number dropped down to 3,729, then to 2,803 after crawl space sealing, and post retrofit. So once we sealed all the holes, once everything was closed up, we got down to about 1,390 CFM at negative 50 pascals, which is the metric that we used before we drilled all the holes. So about what, 30 or like 60-ish%? Yeah.
And just to answer your question, so all the contents were in the house when we did this, but most of the sealant is in the attic. And we do get essentially some mist in the house, but there's no large particles and they don't damage the contents. So after the sealing is done, we just blow all the excess mist outdoors. So we're able to do this with all the stuff in the house.
And just as precautions, we took all belongings out of the attic, where
Yeah.
a majority of the mist was. We took it out, stored it in the place that was safer.
So is this mainly sealing the leaks in the floor plates and single plates on the top of the walls? Or is it blowing aerosol like throughout into the wall cavities?
We're only gonna seal any leak that's essentially associated with that pressure difference. So any leak between the attic and the house, so even if there's like we don't show it here, but if you had like a light fixture cut into your ceiling or something like that, or like we sealed like some random fireplace leaks, we noticed. So just so if we have.
So that's kind of my question.
Yeah.
So in the attic, you're just sealing leaks between the conditioned space and the attic.
Yes,
And in the crawl space, same thing.
Yeah.
Leaks between the crawl.
and some of those are associated with the walls cavities and some of them aren't.
Got it, thank you.
Yeah.
And so do you know what the volume in the house is, like if N.50 it went from what to what?
Oh, good question. These are like 1,000 square foot houses-ish. So
Okay.
8-foot ceilings, 8,000 cubic
8,000.
feet. Yeah.
Did you have to remove the insulation in the attic at all?
Yeah.
Yeah, we tried.
Okay.
We sort of partially succeeded. We had a hard time. We just did this with some of the insulation in there.
We focused around the perimeter of the house where the walls were. Tim fortunately crawled through and did that.
Yes, we should recognize Tim and Robbie.
Yes.
Tim and Robbie were not harmed.
In the process, okay, good.
Maybe they were.
So did you have to re-insulate afterwards? Did that like ruin the?
No, it was like that, so we just like picked it up and moved it back.
Yeah,
Oh, okay.
yeah, it was I like to say simple, but Tim.
All right, we should probably keep going, we're
Okay,
almost
yes.
done here.
Okay, moving on to the blow-in installation. We pulled in installation contractors. They came in with a blower machine, took our Optima installation and just blew into the existing ones for whatever walls that were not insulated.
And what kind of insulation is it?
Fiberglass blow-in installation. PCM installation, this took up a bulk of our time, so we took the. Pardon me?
Oh, wearing the same shirt.
Our local model right there. Yeah.
You never took it off.
No, it's not the same shirt.
Yeah, it's a different one. That one has a black rating.
So we installed it in a grid-like structure, and we produced diagrams for the homeowner showing where the empty channels were. So if they needed to hang anything such as a TV mount, a picture, what have you, they want to access the PCM.
What happens if you puncture it?
It leaks. Yeah, it leaks, but it only leak up to a level where it was, and the leaks aren't that bad. We've had a couple.
We had one.
We had one in Sacramento that we fixed, but we didn't have to pull up the wall. It leaked a tiny bit, we cleaned it up and. Just showing a completed PCM wall right here. We can see we hit up essentially as much as we can. We avoided outlets. This was a unique case because they had window locks, so we avoided that space right there. And then this is just empty space from geometry limitations. But overall, we're able to get a vast majority of the open space of the wall. And then here's just an example of the diagram that we provide to the tenants. You can see these different measurement marks. This is just a clear indication. Drill here, do not drill here, just to make sure they get avoid leaks. Moving on to the field retrofit and finishing, we added stuff like extenders for the outlets, and we went ahead and like in laboratory test, we just did an entire new sheet of drywall, mudded everything, sanded everything down so it's indiscernible from what it was before, except minus a couple inches. And then we all of the items that we took down. So we're talking the trim, the baseboards, everything that was saved. We didn't have to buy anything new, and we just reinstalled it afterwards. The LA house is a little bit special because their crown molding was plastered, so we couldn't actually take it down. So what we did instead is we installed these different panels, and we designed it such that the homeowner was happy, and we made it we try to make it as aesthetically pleasing as possible. And this was a bit simpler. We just added the PCM, added a framing around it, and added drywall on top of that. So it just looked like kind of like a protruding wall, as you see here. So that takes us to our next steps.
Okay, so as we wrap up this project, we are, one thing we didn't show you today was the finite volume model of the base unit tutorial. We've been really struggling with that. So we're continuing on that. And then as I showed you, we want to run those laboratory results out further. And one of the things I hope to gain from the finite volume model, particularly if we can get it working appropriately, is to understand the impact of those air gaps. Then when we have our Energy Plus simulation as good as we can get it, we're going to run simulations for all 16 climate zones and essentially be able to produce results that say, okay, as you increase the amount of PCM you put in the home, right? Like if you do more walls, how does that impact your energy savings as you go from climate zone to climate zone? And then, essentially also, is the ceiling worth it? What happens if you also do the ceiling? And compare that to a uninsulated baseline wall, and then also what if you just do the insulation, you don't bother with these other improvements. And then finally, we're going to have an analysis of the field site data. We didn't talk about, we showed you the retrofit, but there's also a whole bunch of monitoring going on in those homes, and that's being led by our subcontractor TRC. So they're working on that piece of this.
So
That's it.
So to be clear, what you don't have is you don't have like a wall without PCM and a bunch of data, and then you put the PCM.
We monitored the houses for an entire year before the retrofit happened.
Okay, but
Yeah.
so that's good, but so you have a baseline of the wall, but that's pre-insulation, pre-sealing, and pre-PCM.
Yes, it all happened at once.
Right.
Well, the ceiling failed in 2 homes, so that helps.
Oh. Got it, good. Okay.
Is there monitoring on walls that didn't get PCM at all?
Unfortunately, the monitoring data is not as good as I would like. We don't have any flux sensors, for example, and we have wall temperature sensors and wall cavity sensors in 2 places. So we have some information on wall temperature, but it's just not anywhere close to the level of information that we're getting out of the laboratory and the modeling data. So I feel like at the end of the day, that's going to be our best information in terms of understanding heat transfer. And then I think what we really learned in the field is what does it actually take to put this in? And then I'm hoping we see some like high level energy impacts as well, but that remains to be seen. Thermal comfort, we're also measuring thermal comfort in the field. Yeah.
So you're still able to be able to kind of break it down in a way where it's like, we've done nothing. This is the result for this wall. We added insulation. This is the result for this wall. Kind of because like.
From the models and from the lab data, but you just, everybody loves to see also something happen in real life. And that's what's just so difficult to do because it's so expensive and time consuming and obtrusive to occupants, every time you do something.
But you're able to kind of, I mean, because you know the performance of each of these demonstration homes with nothing.
Yes, but
already.
then the whole package happened all at once, I think is Kelly's point.
Right.
So you can't be able to separate out like what did what, like explicitly.
Yeah.
Oh, we can talk about more.
All right. We'll talk. Yeah, sounds good.
Any other questions? Spencer, I don't have a way to like write back to you, but I'll email you because I would like to follow up on what you said. I don't have that LBNL study that you mentioned. So thank you.
I've got a couple questions. Right time, are you?
Yeah.
Are you finished?
We're finished.
Yeah,
Thank you.
I was curious, from a selfish perspective, we have a small project where we're putting a power supply, we're embedding the power supply in the wall. And so one of the concerns is how much heat is it going to generate? And will it exceed various kinds of limits? And so because it's a power supply converting high voltage DC into low voltage DC, or even high voltage AC into low voltage DC. And it looks like your model will actually handle that, be able to help us in that sort of simulation.
Yeah, I mean, in theory, you could add it to the Fluent model.
Yeah. And you also have a test bed. So you can try.
Yeah, you could throw it in a real wall if you wanted.
Exactly, that's what we're doing. So that's one thing, so that.
Yeah, we're all set up to do that. If you want to collaborate, let me know.
Second thing is, I was at the DOE Building Technologies Office peer review conference last week, and there were several PCM papers or research results being presented there. And some of them were in appliances and some of them were in walls, I believe. But we saw this question now about, well, is it worth doing this when we can actually store energy in a battery and use that energy in other ways?
Yeah, I don't, that's what at the beginning, I said, we don't have the answers for you today. That's where we're trying to get, like, what do you really, you've gone through all this work, how much are we really gonna benefit? And that's one of the questions we want to answer at the end, is this really worth it? And if so, like, what's the most strategic way to use the phase change material in the envelope?
And then I'm worried about the point you said about leaking, because what happens if the second owner doesn't have that information about this weird wall that's been installed?
Yeah, I mean, you could also just use, like, there's all types of surface mount technologies that don't require drilling into your walls. And I think, like, whenever you rent somewhere, you're essentially forbidden from drilling into your wall. So I don't know that but obviously if you had like no awareness, it could potentially be an issue. But the one leak we had turned out to be like kind of not a big deal. So yeah, I don't think it's like a catastrophic problem. There's a question on Zoom about residential applications and what about expanding this to like commercial buildings or buildings on campus. And I want to say that our focus was in residential, just because there's I think one of the interesting things about residential is you have a lot of exterior wall area per like unit of floor area. So there's potentially more opportunity in terms of savings for what you can get. But I mean, there are other studies that look at phase change shields at commercial buildings. There may be potential there. And one of our goals really is to nail down the modeling of this so that you could then expand to looking at other building types. Okay, I think we're gonna wrap up today. But thanks all for coming.
Thank you, guys.